The microphone in. Okay. So perms and coms, order matters if the permutation, combination, order doesn't matter. And right now that's going to make absolutely no sense to you. I put this at the very front of the booklet so we can come back to it and we can look back at it when we start talking about perms and coms. But today we're just going to be talking about the fundamental counting principles. So we're not even reading this, but we will come back to this. And I left it on the front so it's somewhere that we can find quickly. But we're going to talk about the fundamental counting principle first. So you consider a task made up of several stages. If the number of choices for the first stage is A, and the number of choices for the second stage is B, and the number of choices for the third stage is C, etc., then the number of ways in which a task can be completed is A times B times C times however many more. Fancy words, fundamental counting principle. Well, what does that mean? That means if I have something that has multiple parts to it, so we're going to talk about a robot here. It could be anything where it has multiple parts. It could be a number. It could be a word. There's multiple parts to it. What we can do, as long as we know that there's multiple parts and we're only picking one of each part, we can use the fundamental counting principle. So we're going to look into it so it makes more sense. So the first thing we're going to do here is we're going to look at a toy manufacturer makes a wooden toy in 3 parts. So we know here that there are 3 parts to this toy. This board hates me, just so you know. It just changes things on me. It does what it wants. All right, in 3 parts. We have the top part. The top part can be colored red, white, blue, or pink. So we have 4 options for that top piece. Then part 2, we have the middle part, and it can be orange, purple, black. And then we have a third piece, which is the bottom part, and it can be yellow or green. Now, I could blindly tell you, we just do this, 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 we multiply things, and trust me, this is how the answer works. But if I do that, you're just putting sheer trust in someone you've met for a few minutes. So that you should never do. So we're going to go through, and I'm going to show you how we can actually get all the different toys from this. And then you'll see that the fundamental counting principle actually does work, and then you're not blindly trusting me, you actually see that it does work. Now, we're doing a tree diagram. We're doing an anti-gravity tree diagram. So trees look like this, correct? Not our tree. Our tree is going to look like this, okay? So you have to pay close attention and do it exactly the same way as me, because there will be people who don't pay close attention, and you'll do a tree downwards like this on the homework, okay? So we're going to do it sideways, and how we do that is we start off with part 1. Now, we're going to label it part 1, and then we're going to have the colors fall below it. Now, these colors are going to have branches off of it, so you need to leave spaces between the colors, or your branches are all just going to mush together, and it's going to be a disaster, and you're going to be erasing within 3 seconds of this. So, part 1 has red, white, blue, or pink. So I'm going to write red, and then I'm going to leave a little space. I'm going to go white, and by a little space I mean a lot of space. Blue, pink. You might want to write small if you're a large writer. So if this toy only had 1 part, how many different toys could I make? 4. That's it, right? If it had 1 part, 4 toys. That's it. Does it only have 1 part? No. But each part I am picking only 1 color, right? That's why I would get 4 toys, because I'm not picking multiple colors per toy. So part 1, we'd have 4 toys. Part 2 has the options orange, purple, or black. So I'm going to write part 2. And off each of these, I'm going to have 3 branches. I have orange, purple, black. If my toy had 2 parts now instead of 3, I'm just looking at 2. how many different toy options could I have now? 12. You'd have 12, because each of the ones you had before now have 3 more options off of them, right? So that's how we went 4, technically times 3, and we get 12. We agree? That's part of a fundamental counting principle, isn't it? The number of options here times the number of options here gets you an answer, right? So that's part 2. We don't stop there. We don't have 12 toys. We have more, because each one can be yellow or green, I believe. Yeah. So we have part 3. And off each of these, we'll have a yellow or green, which I'm just going to write as a Y and a G because I'm lazy. Every one of those 12 toys had 2 more options for each of the 12 toys. So, how many options total do we have now with the 3 parts? 24. Because we could have a red, orange, yellow toy, a red, orange, green toy, a red, purple, yellow toy, a red, purple, green toy, right? So if we actually count all these end ones up, that would be the total number of different toys. We agree? Which is 24. Now, when 24, you can draw a tree diagram, but when your answer is 100,800, you need a large piece of paper to do a tree diagram that large, right? You're not going to go that route. I did a tree diagram just so you could understand it. Now, how we understand the fundamental counting principle and why the heck we do the blanks is this. So we can only use the fundamental counting principle if we're choosing one from each. So if we're choosing one color from part 1, and one color from part 2, and one color from part 3, we can use fundamental counting principle. If at any point in time I can pick 2 from there, like 2 from part 2 and 1 and 1, I can't use the fundamental counting principle anymore. Fundamental counting principle only works when you pick one of each type. Okay? So, how does this work? This blank, awesome. See, the board's so great to me. It's just not, it just doesn't. So this blank, ignore that. This blank is part 1. And this blank here, when you put a blank down, that means I'm choosing one thing. That blank means I'm picking one color for part 1. That's what that blank represents, okay? Above that blank does not represent what color I'm choosing. Above that blank represents how many colors I'm choosing, okay? So how many options do I have for part 1? How many different colors? 4. So above here, I'm choosing one color, that's what this means, and I have 4 options. That's what the 4 represents. The 4 represents how many options, the blank represents I'm choosing one. Okay? Then we'd have part 2. And I'm picking one color from part 2. That's what this blank represents. One color from part 2. Above the line, though, represents how many colors I have to choose from. So how many do I have to choose from? 3 this time. But I'm still only choosing one, right? That's what this blank means. I'm choosing one of it. I just happen to have 3. Then there's part 3. So choosing one out of how many? 2. Now, the key thing here is if we use the word and, we are going to multiply. If we use the word or at any point in time, we're going to add. Now, and add look like they should go together. They're one letter apart. They look like they should go together. They look like, wow, and add, best friends. Actually, no. And add do not ever go together. And, add, no. So if and can't go with add, and has to go with multiply. It's multiply or add are our options, right? So if I use the word and, I'm going to multiply. What the heck does that mean? Well, if I need part 1 and part 2 and part 3 to make the robot, I multiply, correct? If I need part 1 or part 2 or part 3 to make the robot, I would add. We agree? But if I'm saying or, that means if I have part 1, I have a robot, or if I have part 2, or if I have part 3. I don't want that. I want and. I want part 1 and part 2 and part 3 to make the whole toy. We agree? So that's why the fundamental counting principle multiplies. because you need each of these parts to make the whole thing. And then you get 24. Now here you have 24 different parts. So it ends up being the exact same answer as the tree diagram. It's just not excessively long as the tree diagram. It also works better when you have ginormous answers. Then we're going to flip over. Okay. Here we have a school cafeteria offers sandwiches made with fillings of ham, salami, cheese, or egg on white, whole wheat, or rye bread. So there's 4 fillings, 3 types of bread. Now we can use the fundamental counting principle if and only if they pick 1 filling and 1 type of bread. If they picked more than 1 filling, say that you could have ham and salami or something like that, you can't use the fundamental counting principle. Because that blank means I'm picking 1 thing, correct? The moment you put the blank, it means I'm picking 1, yeah?
So what would you use if you couldn't use?
We're going to use combinations, but it's very end, yeah. So if at any point in time you have to pick more than 1 of each item, you cannot use fundamental counting principle, because that line means I'm picking 1. 1 filling, 1 bread, okay? So here it says how many different sandwiches can be made using only 1 filling and 1 type of bread. If I'm picking 1 of each, I can use the fundamental counting principle. So I'm picking 1, that line means 1 filling, and means I multiply 1 type of bread. Remember that line that you're drawing means I'm choosing 1. 1 filling, 1 bread. I multiply because I'm saying I need the filling and the bread to make the sandwich. Because if not, you'd just have a bread sandwich or just holding some egg salad in your hand. It'd be super weird. All right. How many filling are there?
4.
There are 4. How many types of bread? How many types of sandwiches? Yeah. 4 times 3, which is 12. And if you could visualize it as a tree diagram. You have your 4 fillings, boom, boom, boom. Off those 4 fillings, you'd have 3 branches. 12 sandwiches, right? Every single time it's a written response, we're writing some sort of understanding statement. So how many different sandwiches can be made using 1 filling and 1 type of bread? 12 different sandwiches can be made. The next one, we have to always figure out how the heck what kind of amount of lines do we need? What are the lines representing? That's what we have to think when it's fundamental counting principle. The good thing is this lesson is fundamental counting principles, so you know that everything is the fundamental counting principle. So here we have a Math 30 quiz consists of 8 multiple choice questions. So it consists of 8 multiple choice questions. When we did the robot, there was 3 parts, correct? And we did blank for each part, did we not? How many parts are on this test? 8. Each question is a part, is it not? So how many blanks are we going to have? 8. And each blank represents choosing how many options? 4 on top, but how many options are we actually picking? 1. 1 correct answer, 4 options on top, right? So we would have, this is 1 answer for number 1, and 1 answer for number 2, and 1 answer for number 3, and 1 answer for number 4, and 1 answer for number 5, and 1 answer for number 6, and 1 answer for number 7, and 1 answer for number 8. So that means I'm picking 1 answer, correct? When a multiple choice, you have to pick one, whether it's right or wrong. You're picking one answer. That's what the blank stands for. Now we have to keep reading. It says, each question has 4 choices, A, B, C, or D. So the blank means I'm choosing one of each. The top lists how many options I have. So here it says how many different answer sets are possible. So you think on an 8 question test that you might guess and do well. This will prove that the chance of that is slim to none on an 8 question. Because how many options of answers do I have for number 1? 4. 1 is correct, but the top just says how many options I have. What about 2? Then 3? 4, 4, 4, 4, 4. Some people say that's 4 times 8. That is not 4 times 8. That is 4 to the power of 8, which I remember from period 2 was 65,536. Correct me if I'm wrong, because I'm trying to just remember. Yeah? Okay. So, you're guessing on a test. You have a 1 in 65,536 chance of getting 100% on an 8 question multiple choice test. I would say study would be a better option. So you do think like an 8 question, I got a good chance. No, you don't. You got a real bad chance actually. Studying is better. Now, what if I change the question? So this is how they can change the question up, paying attention. Mrs. Lepp is marking an 8 question test. Okay? She hits over her coffee. Her coffee spills on the last 5 questions and obliterates the answer key for the last 5. Just annihilates it. They're gone. Okay? So how many answers are still on this answer sheet? You would have 3 out of how many? How many questions were on the answer sheet? 8. So I still have 8 blanks if I want to, right? I would still, if I did my fundamental accounting principle. That sounds right. There's really only 3 answers sitting on that page, correct? So some people will tell me, well, the first 3 I know the answers to, it's still 4, 4, 4. No, you know the answers to it. You look down at the page, and the page says the answers are A, C, and D. So how many options do you actually have for the first blank? 1. Second blank? 3rd blank? What about the last 5? 4, 4, 4, 4, 4. So you have to actually think, how does this question work? Because if the last 5 washed away, the first 3 are sitting there. They are what they are. A, C, D, B, D, B, whatever they may be, they are. There's still only one option for each of them. It's sitting there. It's telling you what the option is. So the answer to this one would actually be 4 to the 5. This is just a side note, how they could change the question. Right? Okay. Okay, so this one says, fundamental accounting principle involving restrictions. When solving problems involving restrictions, it's important the restriction is dealt with first. So a restriction in that case would have been the first 3. They were restricted to whatever answers they were. We had to do with them first, right? The ones on the previous page. Okay, now, side note. If I give you black cars of the exact same model, 3 black cars that are all the exact same model, exact same year, means they look exactly the same. Okay? And I put 3 cars here. They're little ones because I can't fit them in the room if they're big. 3 little tiny cars that are the exact same, correct? Now I put them in a row. Then I tell you to close your eyes, cover your ears, blah, 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 blah. And I move the 3 cars to different spots. Would it look any different if they were all the exact same car, exact same color, exact same everything? No, it would look no different because they would be repeating objects. They look the exact same, correct? So that's why in this question, because we're not doing repeating objects yet, in this question it specifically states, in how many ways can 5 different models of black cars? Different models means they're still all black. They could be painted the exact same black, let's pretend. But one of them's a minivan and one of them's a jacked up truck. They're the exact same black. Can you tell them apart? Yeah. So you have to watch. If it says different models, it's just that they're all black, but they look totally different. If I put them here or put them here, it's 2 ways, right? I can move them around, first and second or second and first. It would be different objects. But if they say same model, you have to watch because that means they repeat. They look the exact same. So you have to watch. Here it's different, same. So I would leave myself a little side note if it were me, and I would say if it says different objects, they're not repeating. But if it says same model, that means repetition. That means they look the exact same. Very important, because it does make the question totally different. We're going to be dealing with cases in about 2 days where they will be the same. And what do we do when that happens? So here we have 4 different models of black cars, 4 different models of red cars. Cool. I have, 5 different models of black cars, 4 different models of red cars. How many cars do I have here? How many am I parking? 9. Right? I'm parking 9 cars. Oh, you should have been part of my brain in grade 12 when I did these. I did these terribly. I would park all 5 and 4, and then I'd be like, there's no more cars left to park. You'll laugh, but you'll be with me. So, we're parking 9 cars. We agree? How many cars can park per stall? Not a challenge. How many should park per stall? 1, right? We're not stacking cars. We're not sliding them in side by side. We're not doing any Houdini work. We're going to park 1 in each. So they should be parked next to each other in a parking garage. Okay, so we know we have 9. We have this car, and we're parking this 1, 2, 3, 4, 5, 6, 7, 8, 9, bless you. And we know that every single one of these blanks represents 1 item going there. Correct? We've talked about that the whole time. We'll put a blank, 1 item goes there. Put a blank, 1 item goes there. Put a blank, 1 item goes there. We agree? Okay, cool. We're parking them next to each other. We've got to keep reading. They're parked next to each other in the garage. If a black car has to be first and a red car has to be last. So we know this one needs to be black. And we know this one needs to be red. And there's no restrictions on anything else. And I have to send home to you that these need to be here. Whether they're faint or not, you need to have those dots there. Because if not, you're not showing the operation that's happening, which is multiplication, right? Like, for example, if I have the number, you tell me that's 1008, right? Or I have the number, you tell me that's 1296, correct? So if you don't put dots between them, that's the number 1296, is it not? When in reality, this is what you're meaning. You're meaning 1 times 2 times 9 times 6. If you don't put those dots, you are writing the number 1296. Okay? Does that make sense? You have to have the multiplication symbol. It's very, very, very important, or you'll get docked. Now, okay. I remember doing this question. I specifically remember it has been it will be 22 years since I was in grade 12, and I remember this specific question and how I butchered it. But that's fine. That's what I'm brought to this day. You're welcome. I'm teaching you now, and I couldn't do this in high school. You're welcome. Black. How many black cars do we have? How many options? 5. So am I parking 5 cars here? No. That's 5 options. Last name used to be Wagner. Little Crystal Wagner thought she parked 5 cars there. I don't know. Did I think I stacked them? Like, I don't know what I was thinking. I was like, well, 5 are done. Cool. Then I went to red. How many cars are there? How many options? 4. I don't know if my teacher said options. My teacher was actually a really great teacher. But now little Crystal Wagner's like, well, 9 are parked. I have no more cars left. I'm done. And then I'd be like, well, and then I'd put random numbers in the middle because I was like, I got nothing. So might as well just throw something there. It was really bad. It was awful. So, welcome. You're not in the same boat as me. You should be happy. If you are in the same boat as me, remember I was in that boat and now I'm teaching you. So you'll still be in a good boat. All right. So, there's 5 options. But how many cars did I park?
1.
Okay. I have 9. I feel like I'm a magician. I have 9 cars to park here, correct? I parked 1, did I not?
Yes.
Watch this. Whew, how many cars do I have left to park? Okay. Now here, I actually had how many options?
4.
Did I stack all 4 cars there?
No.
No, you're not nearly as foolish as I was. That would be stupid. So we have 4 options, but this blank means I parked how many cars?
1.
Woo! How many cars do I have left to park?
7.
So great. Way better than me. So I go to this blank and I'm like, dude, how many options of cars do I have to park here? What did you just answer me? It's going downhill. It's going downhill. I had you. I had you and I lost you. You all fell off the wagon. Bringing you back on the wagon. Okay, I parked a car. I parked a car. I parked 2 cars. I had 9 cars. I have 7 cars left. So I have 7 options to here. Correct? Because I parked one here, I parked one here, I had 9, I now have 7 for that blank. We agree? Now, that's 7 options. I'm not stacking 7 cars up, because that would be an aggressive amount of cars right now, and they'd be stacked. It would be bad. Okay, now how many cars have I parked?
3.
3, because each of these blanks represents a car being parked. We agree? It's a parking spot.
Yeah. Yes.
Only one car can park there. You guys told me this.
Yes.
I parked 3 cars. Out of 9. How many do I have left for this one?
6.
Oh, goodness. We're bringing you back. Then I park 1.
4.
Then I park 1. How many options left? Then I park 1. Then I park 1. Did I care to separate them as red or blacks at that point? No, because they can be whatever the heck they want. Now, you can viciously type 5 times 7 times 6 times 5 times 4 times 3 times 2 times 1 times 4. You can. Or there's this magical thing called the factorial symbol. It's magic. So if we take little black and little red here, we put them together, we have 5 times 4, which is 20. We agree?
Yeah.
That's a true statement? Remember, multiplication is a commutative property. You can move anything around when it's multiplication. You're going to get the same answer. Like if you do 5 times 3 times 4, and then 4 times 3 times 5, you get the same answer. We agree? So that's why I can just pull this 5 and this 4 out and call it a 20, because 5 times 4 is 20. Now there's this great thing, if you can rocket count. So I can go 7 times 6 times 5 times 4 times 3 times 2 times 1, blast off, and the rocket took off. We agree? True statement? The rockets work? I know nothing about rockets, but I do know that they blast off at the end of the 1. You're all looking at me like you don't know. I did not lose you at the blast off part, did I? Scared for a second there. I lost you when we said 7 and then you were answering 8 and 1 at that blank, and that scared me. So I'm glad we're all back. We're back. Okay. 7 times 6 times 5 times 4 times 3 times 2 times 1, blast off. Cool? So we can write 7 blast off. Blast off is the factorial symbol. It's this magical thing that does all the math for you. It literally types 7 times 6 times 5 times 4 times 3 times 2 times 1 for you. Yeah? Yeah, you're there. It's a great moment. Life-changing. So, where is that button? Where is it?
Math.
It's in math.
POV. And number 4.
Yes. But so we're going to go 20 times. Everyone's doing it. 20 times. I'm waiting for this thing to show up. It's taking so long. So we're going to go 20 times 7. And then I need the factorial button, the blast off button, correct? So I go math. Now you can arrow 4 to the right. You can arrow to the left to get you there faster. I'm lazy, so I'm going to go short term. I'm going to go left. And this is where we're going to sit for this unit. It's either going to be 2, 3, or 4. Well, we need the blast off button. So we're going to press 4. And poof, we get an answer. Or we can go 5 times 7 times 6 times. Ooh, that is a subtraction sign. 5 times 7 times 6 times 5 times 4. That came down from the heavens, right? So we are at a really large tree diagram. That is where we are at if you're tree diagramming it. Like that's not going to happen, right? So parking these 9 cars with a black car in the front and a red car at the back is 100,800. Okay. Pencils down. We need brains. All the brain matter we have. Pencils down, calculators down, brain matter up. We are going to talk about 4-digit odd numbers. You're like, you had to put a pencil down for that? Yeah, you did. Okay. 4-digit odd number. Now, I've always asked this and never ever saw this coming. I would say, how do you know something's odd? And everyone would say, it's not divisible by 2. And I'd say, true fact, not helpful. But that's how it went. So, we're gonna bypass that answer because it's happened for the last 10 years. So I know what's coming. I know you're going to say not divisible by 2, which is a really good fact, but not helpful. So, if I give you the number 32, even or odd? Cool, you're passing. Okay, what about 75? Okay, make it hard. 1,961. Cool. 1,975,463. Okay, you're doing good. Ready? 700 billion, 964 million, 575,302. Because you don't give a crap about anything but the what? The last digit. That is what's important. What does the last digit have to be? Odd, and not divisible by 2, and I didn't hear the other answer, but I'm going to pretend it was right. I believe in you. So, cool. We know the last digit needs to be odd. And it's a 4-digit number. Okay? 4-digit number means I need to have 4 blanks, because each of these blanks holds how many digits? 1. Every blank holds 1 of something. They're all going to hold 1 digit. So this is what we need to know. If it says odd, we know the last digit needs to be odd. True fact. Okay, if it says 4 digits, it says on here there's more information. They will never do this on a test, but he's been told that the number 5267 is a 4-digit number, whereas 0267 is classified as a 3-digit. They're not going to be that nice. They're going to say 4-digit number. 4-digit number means the first digit can't be a what? 0. If the first digit is a 0, it's actually a hidden 3-digit number. If you don't believe me, I will tell you that I will pay you in a 4-digit number. I will pay you 0672. You'd be like, that is 3 digits, and try again. Well, you would not accept that because that is not a 4-digit number. That is a hidden 3-digit number. We agree? So if it says something like a 4-digit number, they're indirectly telling you the first digit can't be 0. Cool, we have 2 restrictions. If we're finding all the 4-digit numbers in the world, it doesn't say anything about not being able to repeat, right? So we could have 1111. That would be fine. Or 9511. That would be fine, right? We're allowed to repeat, because the only time we can't repeat is if it says you cannot repeat, which was not stated in here at all. We do know that the back digit has to be odd. We also know that each of those blanks can only hold a 1-digit number, correct? That's what a blank can only hold 1 number. The 1-digit numbers are the numbers from 0 to 9. We agree? Once I hit 10, 10 is a 2-digit number. 10 is 2 1-digit numbers, is it not? So in each blank, I can only have 1-digit numbers. So on the bottom, I always list what my options are. On the top, above the blank, is always the number of options that can go there, not the number that goes in that blank. How many options? Remember? Like when we were talking about the robot, the first blank had 4 options because there was 4 colors, correct? Above the blank is always the number of options. So I'm going to go to the very back one because I have to deal with restrictions first. And this has to be the number 1, 3, 5, 7, or 9. Because it has to be an odd 4-digit number, my back number has to be odd. We agree? So those are all the options. This blank means I'm only choosing one of them at a time to make this number. The top above it says how many options I have. How many are there? There's 5. Does that mean I left the 5 there? Does it mean the number ends in a 5? Nothing like that. It just means there's 5 options, correct? Okay, 4-digit numbers. The other restriction that everyone has to remember is that the first number can't be a 0. We agree? So it can be the numbers what? 1 to 9. So I list the options below, and I list how many of them are above. So how many numbers are there from 1 to 9? 9. Worst case scenario, you tell me 8 or 10 and don't use your fingers. I would rather you go 1, 2, 3, 4, 5, 6, 7, 8, 9 and know there's 9. Trust me. Any day, any time. I would rather you do that. Were there any restrictions on the middle numbers? What numbers could they be then if there's no restrictions? 0 to 9. Okay, I was always good to this point when my teacher was teaching it. I was like, I follow you. 1, 3, 5, 7, 9. 5 options. 1 to 9. 9 options. Got you. I'm following you, teacher. You were rocking it. Like, that's what I was thinking. Then I got to this moment, and I put a 10 up here. And then I was like, you just told me, teacher, that only 1-digit numbers can go in this blank. And I know you guys think this way because 4 people admitted it in the last class, which means at least half of them were thinking it, because they're not all admitting it. They were in the same boat I was. I was like, dude, you told me 1-digit numbers can only go in here, and you put a 10 up there. Is the 10 the number that's actually in that blank? No. 10 is the number of options that can fit in that blank. I'm not putting a 10 here. There's 10 options. 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9 can fit here, right? 10 options. This would be 10 options. I'm just multiplying the options. I'm not putting the number 10 there. I'm not putting a 2-digit number in there. That is the number of options. Does that make sense? Were there a few of you who were thinking the 10 shouldn't be there? Yeah. With me. Seriously, I remember it from high school. It's been a long tick, but I remember this. I also remember doing slope wrong. So when you do slope, this was in grade 10. I remember distinctly bad math when I did it. But and you remember a slope, you do y2 minus y1 over x2 minus x1? That's what slope is. It's y2 minus y1 over x2 minus x1, and you label your court. You're all like, what? Grade 10, you learned this. I know you did. You're all giving me this look like you never did. But you did. Welcome to grade 10. Anyways, you had two coordinates. You had like 3, 5, 8, 6. And then you would do m equals y2 minus y1 over x2 minus x1. This has nothing to do with this curriculum, but it is something that I want to prove to you. So what do you label your coordinates? X and y, right? That's what a normal human would do. You would go x1, y1, x2, y2. This was a daily quiz or a quiz on sloping. Sloping is a thing. It's an action word. So what did I do? Do you think that that's going to end in good things? Not one, I got a 0 on that test. Not even like part marks, because like you don't label that right, you're getting nothing. 0. The only thing I had labeled correct was the x1 and the y2 just by chance. Like it was just stupid. Anyways, fun fact. 4,500. 4,500. My point in this is you can make stupid mistakes and still be fine. I did this. I survived. I'm teaching you now. It'll be okay. All right. B. Are we ready? This is where you got to put your pens down. We got to really bring it. Okay. So in my first 10 years of teaching this, I did not do this move, but I've learned it's the move called the box and hold. I've made it up. It's mine. I don't know if someone else does it, but I'm going to completely take claim to the fame. So this one has, Eric has now been assigned the task of determining how many odd 4-digit numbers there are. We did that already, correct? That was just what we just did. We just literally did that. But then it says, which have no repeating digits. So that means now the number 1111 out. The number 1152 out. The number 1521 out. Like all those cases are gone. Can't have any repetition. We agree? There's got to be a better way than coming up with all those cases, because you're going to miss a few. Right? Like I would. Just even with the ones, you get so many different options. Correct? So when it says that you can't repeat, I immediately do a box and hold. I will box and hold numbers along the way, so it forces me so I cannot use that as an option in another blank. Okay? So we're going to start this the exact same. The only difference is we box and hold. So 4-digit odd numbers. Still, my back number can be what only? 1? Yeah, there's 5 options. It can be 1, 3, 5, 7, 9. Cool. That didn't change. Nothing changed there. The catch is now that I'm not allowed to repeat any numbers. We agree? When it says you cannot repeat, I box and hold a number. So you can hold 1, 3, 5, 7, or 9. You can pick whichever one you want. You just can't use it again. And because I'm lazy, I pick either the 1 or the 9, because then I can make my number selections easier after that. So I'm going to pick the 9, but you could pick any of them. You box and hold a number. We're boxing and holding one. I'm going to box and hold the 9. So I'm pretending I'm keeping the 9 there, correct? You could pretend to keep the 7, the 5, the 3, or the 1. It doesn't really matter. But now in the first blank, can I use the 9 now? No, that option's gone, right? What else can't I use in the first blank, just from the rules of before? No? 0. It can't start with a 0 or be a 3-digit number. We agree? So it can't be a 0, and now it also can't be a what? 9, because I'm holding that one there, because I can't repeat. We agree? So it can be 1 to what? 8. See how I hold the 9 because I'm lazy and I can just write 1 to 8 now? If you hold a 5, you just be like 1 to 4, and then whatever I was holding a 5, 6 to 9. You can do whatever you want. Okay? But before I move on, I have to do what? Box and hold something. So I'm going to hold the 8. How many options is 1 to 8? 8. Okay. Most of them are good to this point and then fail miserably on the second blank. Let's see if we can do this. So I'm boxing and holding what? The 9 and the 8. What do I have left?
0 to 7.
0 to 7. Everyone will tell me 1 to 7, and they'll forget the 0 can come back. Because the 0 couldn't be in the back blank or it would be even. The 0 couldn't be in the front blank or it would be a 3-digit number, correct? So most people are following patterns, so they'll say 1 to 7, and they'll tell me this is a 7. That answer will be on the diploma. That answer will be on your unit test. Putting a 7 there, because that's the most common picked question answer out of all of them. Because everyone forgets that it's 0. Now the easiest way to remember the 0, knowing it's 0 to 9, is to say, okay, I used up the 9. I used up the 8. What do I have left? If you ask it that way, more people will say 0 to 7, because you've used up the 8 and the 9. They'll remember to bring the 0 back. So you have to think about it that way. What did I use up? I used up the 8. I used up the 9. So now I have 1 to 7 and 0. 1 to 7 and 0, which is 8 options. And then what do I have to do? Box and hole. And then 1 to 7 is 7. So I used to have 4,500 odd 4-digit numbers in the entire universe. That's the maximum amount I could have. And when I take out the repetitions, I have 2,204. So it knocks it down quite a bit, and it should, right? You're taking out every repetition. We're going to skip example 6. And we're going to come down to example 7. So example 7. James wants to travel from Pitland to St. Luke's. How many different routes are there from Pitland to St. Luke's? Now he's traveling from Pitland to St. Luke's once. He's not like looping back 800 times, like, I forgot my wallet. Like, he's not doing any of that. He's like going from Pitland to St. Luke's, right? The top one just says, hey, he's going from Pitland to St. Luke's and he's stopping at Queensville or something. The Queenland or whatever it may be, okay? Or he could go this route, Pitland to St. Luke's, and he's stopping, I think they called this Rutherford at one point, okay? So they're going through those spots. We agree? Now, do I have to take these paths and these paths, like a path here and a path here to get me to S, or could I just take this one or this one to get me to S? Is it and or? Do I have to take a path here and here to get me to S, or a path here, or a path here and take me to S? It would have to be and. If it was or, we're time traveling. So if it's or, we're taking either this one or we're taking this one, which means we'd have to time travel to get us to Q or past Q, right? So we know it's and, so we know we're going to have to multiply. Now, how many paths are we going to take from P to Q to get me to S? How many of these paths are we going to take? 1. We're not going to take 2. We're not looping back, correct? So we're taking 1 path. Remember, this means I take 1 path. That means that's why I can use the fundamental counting principle in this question. I'm taking 1 path from P to Q. Above that line, I say how many path options I have. How many options do I have? 2. Now I'm taking 1 path from Q to S. How many options do I have? 3. So how many total do I have? Just in case you were wondering, my weekly goal is complete on my Fitbit. I know you were all concerned about that. Why is a weekly goal done on Tuesday? I'm just so fit. That's why. Sorry, I just forget about my fitness. Okay, and then P to R, we're taking 1 path. How many ways is there? How many options? 3. And then this one, how many options? 1, and we're multiplying them, so this is 3. Now, most people can get here. It's the answer that it's like, is it 9 or is it 18? Is it 9 or is it 18? Both options will be there, so you need to know your stuff, right? So we need to make it make sense. So, if it's 9, we're saying or, because we're adding. If it's 18, we're saying and we're multiplying. So let's think about this. So are we taking these paths or these paths to get us there? Or are we taking these paths and all of these paths to get us there? Is it or and? Or. We're going to add them. We're taking 6 paths, or we're taking these 3 paths, so we're taking we have a total of 9 paths. Not 18. If we say 18, we're literally taking all of the paths. We were spending days to get there. The homework for this is going to be tomorrow, so you don't have any